Today I'm gonna be explaining an important article. We are fixing the max product in this article in 27. And there is an obvious relationship between between message passing and LP relaxations. For example, this is a new research area because people found that, for example, your variables in Lagrange multipliers are related to messages in your message passing algorithm. So it's really important to discover these things. So the idea is similar to max product, but unlike max product, it always converges and can be proven to find exact map solution. So the algorithm is derived via block coordinate descent. This is important in optimization. You decompose into two set of variables, and you fix some of them, some blocks, one block, and you work on the other block. And finding the assignment with highest probability in these models is key to using them in practice, and is often referred to as the map assignment problem. In general, it is NP hard with complexity exponential to 3/5 of underlying graph. And this is an example for map assignment. You have, for example, you have three variables. Each variable could be either 1 or 0. And if I change it to, for example, this configuration, this is another assignment, another configuration. It has another probability. And so there are three approaches to map assignment. You either use LP relaxation or max product, or in this paper, it's a combination of both max product and LP relaxation. And we work on that as both edge and node. We consider both of them. You know, LP relaxation have proven very useful in approximating the map problem. These approaches relax the constraint. So when the LP solution is integral, it is guaranteed to be exact map. So the relation between max product and LP relaxation has remained largely elusive. People still write papers about it. Although there are some notable exceptions, for example, for tree-structure graphs, we know that max product and LP yield the exact map. The max product algorithm is one of the most often used methods for map problems. Although it is neither guaranteed to converge the correct solution or in fact converge at all, it provides satisfactory results in some cases. So there are some advantages of using MPLP. You know, it's a combination of 1 and 2. It becomes 3. First of all, after each iteration, the messages yield an upper bound on the map, which is nice. There are no additional parameters. If the fixed point beliefs have a unique maximizer, then they correspond to exact map. And for binary variables, MPLP can be used to obtain solution to LP relaxation of the map problem. So this is a map problem. You know, these are constraints that we use for consistency, making sure that for each node, for example, we have selected just a unique label. And this is interesting. For example, label 0 is assignment. We put it with 1. So it's a long list of 1 and 0 is a vector. And you consider all of these constraints. Some of them are unary constraint and the rest is binary constraints. Because these make sure these work on edges and these work on nodes. And this is a good example that you will see how you can create this mu vector. And you know, we go to the dual because we know that this argmax, when you multiply it by theta, the product is always greater than your f. So it's an upper bound on the map value. So when the optimal mu I have only integral values, when you found that mu I are some integral, the assignment that maximizes yields the correct map assignment. We make sure that they are the correct map assignment. And here is the proposition that is proved in this paper for convex dual of that. And also this proposition is proved in the appendix of B, appendix B. The lambda updates result in a MPLP algorithm, which is described here. You see, in max product, we iterate until a stopping criterion is satisfied. In max product, we iterate over messages and updates. So we are iterating you know this very well. In EMB, E stands for edge, ENLP, and N stands for node, and this is edge. For edge MPLP, we update the lambda and simultaneously, we update them simultaneously. And for the node MPLP, iterate over nodes. And finally, we return the assignment X, because at the end of the day, the assignment is important for us. We can calculate the argmax of B because we know the Lagrange variables.